Okay. So good evening to all of you. I invite our department faculty member, Dr. V. Satish Kumar sir, to give introduction about our today's speaker, Professor Tang. Over to Satish sir.
Thank you, ma'am. So it gives me immense pleasure in welcoming Dr. Jinshang Tang. He is a professor of health informatics in the Department of Health Administration and Policy. So before joining George Mason University, Dr. Tang was a full professor in the College of Computing at Michigan Technological University and a founding director of the Joint Center of Biocomputing and Digital Health. Research interest includes biomedical image analysis, biomedical imaging, artificial intelligence in medical science. So professor has obtained over $3 million grants as a PI or co-PI and has published more than 130 plus refereed journals and conference papers. Professor is a senior member of IEEE and a co-chair of the Technical Committee on Information Assurance and Intelligent Multimedia Mobile Communication, IEEE SMC Society. So it is a great privilege to have you, sir. So today, Professor will be delivering a talk on automatic detection and segmentation of COVID-19 infections from medical images with deep CNNs. Over to you, Professor.
Okay. So can I start now or start at 9?
You can start, sir.
Okay. Okay. Thank you everybody to come to my presentation. My name is Jinshang Tang. As you just told everybody, I worked in Michigan Tech before I moved to George Mason. Most of this work was done when I was a professor in Michigan Tech. In fact, during the COVID-19, I moved to George Mason at 2021. So the presentation is about my research during my work on COVID-19 period. The topic is about detection and segmentation of COVID-19 infections from medical images with deep CNNs. Everybody knows the COVID-19 affect the whole world. In fact, during the from 2009 to 2004, the whole world was taken over by COVID-19. As everybody now knows, COVID-19 was caused by SARS-CoV-2, a new virus. Also, everybody knows the first cases were identified in people with pneumonia in Wuhan, China in late December 2009. In fact, after that, it quickly spread to the whole world. Also, the WHO declared the situation a pandemic on March 11, 2020. In fact, as everybody knows now, COVID-19 caused severe illness and death. It features sustained person-to-person spread worldwide. It poses especially high risk for the elderly people with pre-existing health conditions such as high blood pressure, heart disease, lung disease, diabetes, or the immune disorders, and certain workers. In fact, during the COVID-19, I also gave a presentation. I get a screenshot at that time. So if you guys see the picture here, it's not the picture for now. is the old one. I used the old picture to just show, even at that time, the case is very, very big. In fact, till now, everybody knows there are millions of people died of COVID-19. So at that time, the main ways to fight the COVID-19, what my research at that time to use the medical image to find against COVID-19. In fact, medical image in the early stage played an important role in the fighting against COVID-19. Also in the early stage, many countries, including China, USA, they also use the CT and MRI and even X-ray, this kind of medical image to detect and diagnose COVID-19. Also, many countries use this technology to evaluate the treatment of COVID-19 to see whether the person is recovered or not. Also, whether there is a white non-infection or something. Generally, it's a white non. That means that's very, very serious. In fact, the major modality most used for COVID-19 was CT and X-ray. In fact, when the people use CT and X-ray long time ago, also the many research on focus on the AI to find against COVID-19. In fact, the pandemic has forced healthcare providers and governments around the world to accelerate the development of AI tools and scale up their use in medicine. At that time, National Institutes of Health, is called NIH in USA. They launched the Medical Image and Data Resource Center, an ambitious effort that harnessed the power of AI and medical image to fight COVID-19. The midrock goals were to lead the development and implementation of new diagnoses, include machine learning algorithms that allow rapid and accurate assessment of disease stages and helped physicians optimize patient treatment. At that time, I did my lab to focus on the medical images with the AI technology. It's matched the deep learning technology to detect and diagnose the COVID-19 disease. What I report here is a partial work of my research using AI to fight COVID-19. The research is about automatic detection and segmentation of COVID-19 infections from medical images with deep learning technology. The aim for this research is to allow rapid and accurate assessment of disease stages and help physicians optimize patient treatment, detections, segmentation of COVID-19 infections from medical image. That's the aim, because at that time, there are many this kind of medical image data there. Also, sometimes even the doctor sometimes some place doctor, they cannot identify is COVID-19 or not. So we try to focus some research to develop AI tools to do that. So some people in some region which does not have too much experience, they still can detect the COVID-19 infections. From the infection areas detected and segmented, we can extract features to assess disease severity. Also can be used to predict response to treatment, thus improve patient outcomes. These features include the size of the infection areas, the density of the infection areas, and so on. So this picture just show a CT scan of lungs of COVID-19 patient with areas described by radiologists as resembling grains of ground glasses. You guys see this kind of areas is COVID-19 infections. What's the basic idea? In fact, our basic idea is you have the original CT images, then we can extract these infections. Then also we can use the area, the size of the area to evaluate whether the infection is severe or not. Also, we can evaluate the treatment because the change of the size of the infection, if it's become smaller and smaller, that means the treatment is effective. Okay. So this is the Gentry framework. You have original image. Okay. So the first step, we need to segment the pulmonary parenchyma. Okay. This area. Okay. Because the infection, they should be inside this area. So that's the first task. After that, we need to determine whether there is COVID-19 infection or not. In fact, this is a yes or no question. Okay. In fact, this whole three step for the determine whether there is COVID-19 infection could be used to replace RT-PCR test for COVID-19 screen. In fact, in the only stage, the many country they do use this CT to find whether there is COVID-19, because at that time the RT-PCR test are not available in some area. So we generally use the CT to replace the RT-PCR test. So this is for determine whether there is COVID-19 infection. After we found there is COVID-19 infection, then the second task is to segment the infection area. From the infection areas segmented, we can extract the features such as size to assess disease severity. Also can be used to predict response to treatment, thus improve patient outcomes. So we have three tasks here. One is segment the parenchyma. Okay, this is the first task. The second task, you need to determine whether there is a COVID-19 infection. The third task is to segment the infection. Let's talk about the first task, to segment the parenchyma. Okay, how to segment the parenchyma? This is the region image. Okay, we could segment out the parenchyma. Okay, because my research is focused on the deep learning, so we developed a deep CNN method called SPVNet to perform parenchyma segmentation. Currently, in fact, the segmentation, there are many segmentation now. There are many UNet, UUNet or something. But at that time, we don't have too much tools available. So we developed our own net to do that. This is the structure of the SPVNet. It's based on the VNet. Okay, VNet also is a method developed by some people. It's a little different from the UNet. Okay, our SPVNet is based on VNet, but we put the shape deformation module in the VNet so as to optimize the weights of the VNet and improve the performance. The shape deformation module is implemented by spatial transform network called STM. This shows the structure of our SPV net. In fact, it is composed of two networks. First is this part. Okay, this is the standard 3D VNet. Okay, this part is called the STN net. It's a shape deformation module. Okay, we have a north here is for the VNet. Okay, but also we put the shape pro here at the input with the original image. Okay, this is the property map. Okay, then this is the ground truth. So the north is the between the property map and the ground truth. Okay, we will see the function, loss function later. Okay, for this side is a STNet. Okay, STNet also we use the probability map and the shape probe as the input. Okay, then also we obtain the deformed probability map. Okay, the loss function is between this map and the ground truth. Okay, here inside here there is a fun transformation. Okay, so this is the basic structure. We already published one paper on the SPV net. So this is show the two loss function. The first loss function is called sigmoid cross entropy loss function. Okay, it's used to training the VNet. The second loss function is used to training the STN network. So the total loss is them together. Definitely, you can put a weight between these two loss functions. For example, this could put the W1, W2 here. Okay. How to training this network? In fact, we have two steps. First step is training them separately. Okay. For example, we first training the VNet independently. Then we training this one. Okay. So let's show the basic idea. Okay. So the inputs is the CT volume. Okay. Also the predefined shape point. Okay. So in epoch 0 to epoch 0.2 E, okay, we training the VNet, while fix the weights of the STN net, use the loss function defined in equation 1. That means the STN's weights are fixed. Only the weights of VNet are changed. So we training the network. Then in epoch 0.2 E to epoch 0.4 E, we training the STN network. During the training of the STM, we also fix the weights of the VNet. Okay, so this step 1, step 2, in fact, it's just the training one of the two networks. In the step 3, in epoch 0.4 E to epoch E, okay, we just training the whole SPV net. Use the combined loss function defined in equation 3 is here. Okay, so the benefit is that the multi-step training can make the training converging fast. Okay, for example, this show, the year-long show is the baseline of the SPVNet training process. But the blue line is a multi-step training. You will find the multi-step training converge very fast. Okay, so that's the benefit. So after we training the network, we use it to segment the slice. Okay, we compared with the VNet. So this is the CT slides, original one. Okay, the first 3 are the COVID-19, but another 2 are the slides without COVID-19. Okay, so this is the ground truth. Okay, this is the result obtained use our network. Also, this obtained by the use of VNet. If you guys see this 2 result for the VNet, the segment is still small stuff inside the camera carocema. Okay, so that's not good, because what we really want to get is the boundary. Okay. This just show the virtual pictures. We also need to quantitative evaluation. We use several metrics to evaluate. One is the dice, okay, dice similarity coefficient. In fact, this one is often used for the segmentation evaluation. We call it DSC. DSC merges the proportion of the interaction between the voxes extracted by our segmentation model and the voxes in the ground truth. That means if the overlap of these two are big, this number will be big. That means your segmentation is good. Beside this one, also we use the surface dice similarity coefficients. We call it SDSC. SDSC merges the surface distance instead of the volumes in our study. Because you guys know, if you see the see this stuff, in fact, is a parenchyma. Parenchyma, in fact, is we need to extract the boundary. But this is 3D image, so the boundary organized is a surface. So we really want to evaluate is the surface. Inside, that's not important. What we really want to get is the boundary. Okay, so we just use the surface to compare the result. That's why we use the STSC. Okay. Beside the DSC and the STSC, we also use the sensitivity, okay, and specificity. Sensitivity merges the proportion of the true positive voxels that are correctly detected. That means it's true, then we detect it. SP merge the proportion of the true negative voxels that are correctly predicted. Okay, so that's the quantitative metrics to evaluate the segmentation algorithm. In fact, we compare our method with several other methods. Okay, one is VNet, one is MC VNet. Okay, so the cohort include the result for only COVID-19 and also for the CAP. Okay, and also for the HC. Okay, CAP here means community acquired pneumonia. HC means health controls. Okay, so if you guys see the value for different metrics, okay, also beside the NSP, DSC, SDSC, we also use the Hausdorff distance, also the mean average surface distance, two other two metrics here. Okay, so if you guys see the red one, that means is the best performance. Okay, if you guys compare our network with the UNet, in fact, everything is better than the VNet. But to compare with the MC VNet, if you guys see here, only the SP for MC VNet is better than our network. Other metrics, our method is better than MC VNet. So this result show that our method worked better than other two. Okay. Also, we also compared with the simple threshold method. Simple threshold method is not very good. Okay, it's worse than all of the three deep learning burst method. Also, we visualize the surface distance of the segmentation result. Okay, for this one is the ground truth. Okay, for three type of non-staff. Okay, so if you guys see our method here, okay, the second is our method. This is VNet. Also, if you guys compare this place, okay, here the segmentation, the yellow here is not good. Also see here the two meaning, red here also is not good. The green it means good. Okay, so that means our method also has good visualization. So that's the first task. Okay, the first task we segment the parenchyma. Okay, after you segment the parenchyma, then we need to detect whether there is a COVID-19 infection inside this area. Okay, so the next step is determine where there is COVID-19 infection inside the parenchyma. Okay, that's our task 2. After that, we can go to the task 3. Okay, so we will focus on task 2 now. Task 2 is to automatic detect COVID-19 infection in the CT image. As I told you just now, automatic detection of COVID-19 based on imaging could be used to replace RT-PCR test for COVID-19 screen when RT-PCR test is not available, or when the fast tests are required. Because in sometimes the RT-PCR test takes about 2 or 3 times. Okay, even now, when I go to the CVS in USA, sometimes I go there to get something, then will tell me later, 3 days later. Okay, there is some fast test now, but the fast test sometimes the accuracy is not high. Okay, but in the early stage of COVID-19, many region the RT-PCR test is not available. Okay, but they do have CT machines. Okay, in the hospital. So in many hospital, they do use the CT or X-ray, even X-ray, to detect COVID-19 infection. In fact, the automatic detection of COVID-19 based on image can be combined with PCR test when the accuracy of RT-PCR test box is low. Okay, if both of the way found COVID-19, that means the person has the high probability of COVID-19. Generally, automatic detection of COVID-19 based on image is mostly used for pre-screening or complementary tests. Okay, especially now. Okay, after you have this kind of RT-PCR test, then sometimes with seconds they will still need to also do some COVID-19 examination. At that time, we developed a framework for the detection of COVID-19. For example, after we segment the parenchyma, okay, then we extract the rhythmic feature from the area, okay. Then we use the logical regression, okay, to find whether the future is good or not. Okay. Then we use the test to select features. Okay. If the p-value less than 0.05, then that means the feature is significant, then we keep. Okay. After we select a bunch of features, also we do the correlation analysis. Okay. Then we just remove the highly correlated features. Then we do the market analysis to select more powerful features. Then we put to the classification. Then we determine was that COVID-19 or not. Okay, I will explain them in details in the next several slides. First, let's talk about the feature extraction. In fact, we extract 85 features from the non-region for the univariate analysis, include the Green-Neighbor size zone matrix, Green-Neighbor co-occurrence matrix features, and also Green-Neighbor dependence matrix features. First, all the features, median, range, and 19%. For this kind of stuff, you guys can check the Google, found the meaning. Okay, I will not explain them here. Okay. In fact, most of these features are used in machine learning a lot. As I talked, we need to select features because you have 85 features. Some features perhaps are not good for prediction of the COVID-19 infection. We need to find the important features. So we need to select features. After feature extraction, a univariant binary logistic regression analysis was applied to value the potential features for COVID-19 classification. Okay. Use this kind of regression analysis, all the features with p-value less than this value, okay, were selected to construct future set for future analysis. Also, we can say future vector something, okay. After that, for each feature in the selected feature set, we compute the correlation coefficient between this feature and each other feature is a feature set. Okay. If the correlation coefficient was more than a threshold, in our research, it was said to be 0.83. Okay. Then the feature with no AUC values was removed from the feature set. Okay. So this is for the feature selection. 85 feature. At last, we keep a very short number of features for classification. After you get the feature vector, in fact, the next step is to find some good machine learning model. At that time, we test several ones, and we found the simple one is good. That's called multivariate generalized linear equation can get the better result, even better than SVM, random forest, and so on. Okay. In fact, we tried logistic regression model. This one also we tried SVM, random forest, and k-nearest neighbors. Okay, but we found GLM can get the best result. But now there are many people just use the pure deep learning method, and that also can get very good result. But at that time, it's about I remember our work is 4 years ago. Okay, at that time, we just use the simple one, then we get the best result. This is show the result. Okay, you guys see here, this show the future selection. Okay, some method we use feature selection, some not use feature selection. Also, we do normalize of the feature. Normalize just to make the feature value to between 0 and 1. Okay, so for this is show this column show the method. Okay, we test the 5 method. Okay, we just do the feature selection or do the normalization. Okay, then you guys see here the rate number means the best performance. So you guys see here GLM can better the three best performance for three metrics: ACC, SB, AUC. Okay, but the SVM can get it too. Okay, and the SN and the AUC. Okay, but each of them should be okay, or these two. Okay, that's for the future selection and also with normalization. The same for this 5 method for future selection and also but with no normalization. Then also we get this one. You guys will found the without normalization, the performance is not good. It's not better than the future after normalization. Okay. The same also we test the future selection without future selection, but with normalization. Okay. Sometimes also good, sometimes not bad. Also, without future selection, without normalization, we found the performance is very worse. Okay, so that means with future selection and normalization could get better result. Okay, that's our COVID-19 infection detection. So after we detect there is COVID-19, okay, if we don't want to do the infection segmentation, we could stop here to use it for replace the PCR test to test whether the person has a COVID-19 infection. But sometimes we generally go to next step. Okay, after found COVID-19, we want to find what's the size of the area of COVID-19 is bigger or smaller. Okay. Because generally we want to use the features to assess disease severity. Sometimes also we need to predict the response to treatment. Okay, if the infection area shrink, that means the response to the treatment is good. Okay, the final aim is to improve the patient outcomes. Okay, so we need to do the segmentation. In fact, in some hospital, generally they use the human being to detect the area, even now, okay, because some hospital, they don't use the automatic one, okay, or they sometimes they don't trust the automatic segmentation, okay, they still use the human being to do this one. But currently, we found the automatic segmentation is much better than human because it can reduce the labor cost. And also sometimes it's without bias. So when I do our work, okay, well, at that time, when I work on our, at that time, when we work on the project, the existing COVID-19 infection sector method already exist, but most of them require peaks-wise annotation. Okay, that's for each peaks artifaction they need to labeled. Okay, which is label intensity and time consuming. To tag this shortcoming, we propose the non-weekly supervised segmentation for COVID-19 infection, which only requires scribble supervision. You guys see here, this is the render image. For this one is pixel level annotation. That means for a doctor, okay, for each infection pixel, they need to label them, okay? So for example, you need to label all of this kind of stuff. It takes a lot of time, okay? But for the script level annotation, they don't label each pixel. They just label some of the infection area, okay? The red one, okay? Also, we do the label for the non-COVID-19 pixel, Okay, you just very fast to draw curve here. Okay, also for this one, also you can very fast draw low curve, draw curve. Okay, you don't need to label 1, 2, 3 very detailed. Okay, so this is just take about 1 or 2 seconds, but this one is take about 10 minutes. Okay, so the annotation, this one is very fast. Okay, so we use the second one. So because we use this one, so we need to develop different segmentation method. Our segmentation network is called USTM net. Okay, USTM net. The U stand for uncertainty aware. S means self and sampling. T means transformation, and M means mean. In fact, this model also called the teacher model, student teacher model. Okay, we will see the architecture in the next slides. Okay. The benefit for this method is that use square level annotation instead of pixel level annotation in COVID-19 segmentation can reduce label cost. Okay. We use the uncertainty aware mean teacher model. It can encourage the segmentation prediction to be consistent on different perturbation for input image. Okay. In next slides, we'll know the mean teacher model can guide the student mode training with the usage of information image in images. Also, in this network, we adopt transformation consistent strategy. Okay, and this is used to regularize the model with transformation consistent strategy. Okay, this is beneficial for the segmentation task and make our approach easy to deal with segmentation of irregular nation areas. For this one, we have a application in the pattern recognition. If you want to know details, you can go to our paper. Okay. So this is show the framework. Okay. This is the original CT slides. Okay. So you guys here, there are two models here. One is the student mode, one is the teacher mode. The student mode is the model we need to be trained to segment the original image. At the same time, we put another model, teaching model. Okay, teaching model is guiding the training of the student model. When after training, the teaching model will not exist. We just have the student model. Okay, that's important. Okay, that's important. So the model is like this one. Okay, you have original image. Okay, this original image, we do the noise. Okay, change the noise are add here. Okay, we get the new noise the image. After that, we through the student model. Okay, after student model, we have transform. Okay, the transform is just a simple rotation. Okay, for example here. Okay, rotation. The result could be rotate 90 degree. Okay, you guys see here. Okay, for example, this is the ground truth. Okay, for the ground truth, we also do the same transform here. Okay, to rotate like this one. Okay, this is for the student mode. For the teaching mode, first we add noise. Okay, then we do the transform. Okay, transform. That's rotation here. Okay, then put the transformed image to be the input to as the input of the teaching model. Okay, then the teaching model. Okay, The coefficient, the weights of the teaching model is from the student model. Teaching model, we don't train it. Okay, we just get the average. Okay, we will show the mass later. Okay, also we have dropout. Okay, then create the uncertainty map here. Okay, then this is a segmentation result from the teaching model. Okay, this is dropout. Okay, output dropout something. Okay, then we get the uncertainty map. So this is the ground truth. This is transformation of ground truth. Okay, do simple rotation. Okay, so also there are two loss here. One loss is LS. This is used training the student model. Okay, of LC is majorly used for compute the difference between the uncertainty map of the teaching model's output. Okay, this one put together, that's the total loss. Okay. In fact, during the training phase, we training the student model. Okay, yi are compared. Okay, it's here. Yi, in fact, is yin with si tutor compared with this one. Okay, use the script pixels. Use the script pixels. Okay, and yi tutor use uncertainty where consider loss. For this one, they use another loss. It's called LC. Okay, the loss only updates parameter of the student model here. Okay, through the back propagation. Okay, the teaching model is not trained. Okay, the teaching model is the exponential moving average of the student model. Okay, so that's just get the moving average, the coefficients, to get the student teaching model. Okay, the goal of the training phase is training an effective segmentation model to segment the nation region in the CT image. So after training, the teaching model part will move. Okay, only we have the student model. Okay, then we have the regional image, then get the segmentation result. Okay, so that's the student model. So that's for the training phase. In the test phase, only the training student network is employed to predict the nations by original image. Note that perturbations and transformation operations are not used in the student model. Okay, and the noise here is for the perturbation. We will know we will add multiple noise here. Okay, noise here. The basic framework for the teaching and student model, in fact, we use is Dyson 2D Dyson ULAT. Okay, this just show the basic structure. Okay, this is the input. Okay, then also we have many convolution layer, pooling layer, Dyson layer here. Okay, also we put a drop out here. Okay, in fact, this is similar to the Dyson ULAT, but we just add the ASP here. Okay, a new module put here. Okay, this shows the translation layer and the Dyson block structure here. Okay, this just shows the ASP structure here. Okay, for this kind of details, I think you guys need to read our paper published in the pattern recognition. Okay, because the detailed explanation. So how to get the weights of the teaching model? As I told you guys, we didn't training the teaching model. We just training the student model. The weights of the teaching model is obtained use the following equation. Okay, every time the student mode was trained, then we get the teacher's model's weights. Use this equation. At the early beginning, the teaching model's weights are the first time. For example, when the student model was trained at the first time, they can assign to the teaching model directly, make the third t minus 1 equal the student model weights. Okay, at the second times, then we use this equation to update the student teaching model's parameter. Okay, epsilon here we choose as 0.99. You could be use other number. Okay, but it should be between 0 and 1. Okay. This is the loss function we use. Okay, we put some weights here. Okay. What's the format of the LS? Okay, is this function. In fact, this is the loss function. Okay. Here, you guys see here, omega is a set of script pixels for image. Okay. LC is here, okay, because there is a uncertain map come from the teaching model from after dropout from here, okay. This is the teaching model real segmentation, okay. Here the UIJ is the uncertainty at the IJS pixel, okay, which is used to merge the consistency of the combination result by the teaching model on different position. In fact, after you have the teaching model, okay, so for this one image, we could add many times noise, okay, then we get different noise the image, okay, then pass through the teaching model, okay, then we get a map, because you guys know we put many noise here, so we could, for example, you put the m times noise here, then we get the m uncertain map. Okay, so the UIJ will computed by the m uncertain map. This is the show how to get the UIJ. Okay. In fact, on the input Gaussian noise and the random and color dropout, let's talk about is one is the how to add noise here. One is about how to drop out here. Okay. So each input image is stochastically passed forward m times through the teaching model. Okay. M times each image passed through the teaching model m times for each time with one add one noise, one type of noise there. Okay. So for each pixel ij on the image, we obtain a set of softmax probability vector. Okay, because we have m map here. Okay, for each pixel, one time with one probability, m times with m probabilities for each pixel. Okay, then because we have several classes. There is a infection, there is a non-infection area, okay, background areas sometimes, okay. So we have generally case we have two classes, Okay, so the C could be 2. C equal to 1, C equal to 2 here. Okay, 1 means background or infection area. Okay, so for each class, we can have a probability. Okay, then we add them together, get the probability for this class, or picks ij. Okay, then for these 2 class, we compute their probability to merge the uncertainty. Okay, uncertainty. Okay, uncertainty get like this one. So if you guys see here, if the certainty is less than some value, okay, certainty, that means unsure. If the probability of unsure is big, then we put the 0 weights here. We don't count it in the loss function. If the uncertainty is smaller, that means the segmentation result is reliable. Okay, then we compute then in the loss function. Okay, so that's the basic idea, to use the script annotation to compute the loss. So we do have some tests for a database. Okay, we do use. I remember we do use several databases. Some data is from the local hospital or something. Okay. This just show the original city image. This show use the UNet. Okay, this use S2L net. This our net. This is the ground truth. Okay. If you guys compare this kind of result, you will find for large and clear infection. Okay, the first and second here. Okay, all the segmentation method can get a relatively good result here. Okay, but for the small infection area, okay, the third line here, okay, or when the boundary of infection area ambitious for the fourth line, okay, fourth line, and generally our method is close to the ground truth boundary. Okay, we do use some quantitative metric to compare them. Okay, this is just to show the result here. Okay, show the result. Okay, show the method. For example, this is S2L method. Also use the PUNet. This is our method. Okay, if you guys compare this kind of matrix, okay, the matrix DI means dice coefficients. For IOU is the interaction over unit, and also J means the guard index. Also AC sensitive, and SP is specificity. Also we have the mean absolute error. Okay, if you guys compare this kind of matrix, we get the best result for 5 this kind of matrix. Only the IOU, this method is better than ours. Okay, this kind of result shows that the proposed method is better than other methods. So that's for the whole segmentation. So this is the task 3. Okay, after we get segmentation, we could use it to find the size of the area to determine the severity of the COVID-19 infection, and also can use it to evaluate the response of the treatment. For example, when the person was infected, we have the size of the area. Then after treatment, 1 week, we get the CT image again and merge the size. If the size shrinked, that means the treatment is very good. Okay, so this is for the use for the for the segmentation. In fact, what we do at that time, the data sets is limited because there are many limitation when you get the COVID-19 data. Because my work was also cooperated with Chinese researcher, some limitation was put by the Chinese government. You cannot get big data. Okay, but currently, if the people want to do the research again, there are many very available open data sets. Okay, so in fact, if you guys want to do, I suggest you can expand to a big data sets. Okay, because our scripting annotation method is very good. Okay, can be used to process big data. Okay, at that time we do the separate way, 3 tasks in separate framework. In fact, in recently our work, we can combine all of the 3 stacks in one framework. For example, we can design a net to do the segmentation for the parenchyma, for the detection of the COVID-19, and also segmentation of the COVID-19. We do have some work in other medical image. I think that framework still can use for the COVID-19. Okay, but if we want to do the whole things in one framework, also I want to extend the big data sets. Generally, we could be use a GPU cluster. One GPU generally does not. 1 or 2 GPU is not good. In fact, when I was Michigan Tech, I set up the GPU cluster before I moved to George Mason. Okay, so the GPU cluster is in fact currently the GPU cluster is much clearer than what when I do my work, because you guys know the language model ChatGPT, all of this big data process, they use the GPU cluster. Okay, the GPU cluster not just 100 GPU or sometimes 1,000. Okay, perhaps 10,000 or something. Okay. So in fact, there are, during my work, there are many collaborate for this one. There is I list some of the people here. Okay. So they work on this project and put a lot of efforts on it. Okay. So also I list the publication here. Okay. Especially for the first one. Yeah. I think I missed the second. The second one also published in the patent regulation. Okay. All of the content is from this 2 paper. Okay. Okay, any question? I finished.
Thank you, Professor. Participants, any questions from your side, please proceed.
I don't have any question.
Faculty members, participants, please go ahead with your questions. Professor is ready to answer.
Yeah.
Any questions from participant side?
No, ma'am.
Participants, any questions from your side?
No questions, ma'am.
Okay, ma'am. Professor, I think no more questions from
No
participant
questions, ma'am.
side.
Any recent research topics in the corresponding field?
Jnana Prakash sir, a little bit louder. Your voice is feeble.
Recent research topics in the relevant area, ma'am. That is my question.
I cannot hear
Professor,
you.
yes, Professor, please.
Yeah. What's your question?
What is the recent research going on in this field, sir?
What's the reason to go on this research?
Yeah.
In fact, when the first time, in fact, as I just told to you, at the early stage, there are not many too much PCR test. So the original, when I developed this project, we want to help the hospital to automatically to determine there is an infection area there. Okay, we cooperate with the hospitals. They use their software to find this kind of. Also, they use it for evaluate the treatment, the response of the treatment. That's the original aim to do this research. They do use our stuff in the hospital. You know, there are several. We collaborate with several hospitals in Shanghai and also in Wuhan. In USA, we also collaborate with one hospital here. So that's the major aim to do this research.
Okay, sir. Thank you.
Thanks.
Any other questions from participant side?
No, ma'am.
Okay. Professor, I hope no more questions from participant side. Professor, that was an excellent and informative session. Thank you, Professor, for accepting our invite and being part of the Subtle Online MTP program. Thank you very much, Professor. Hope participants also benefited. Thank you, Professor.
Okay. Thank you, guys. Okay.
Thank
See you.
you.
Okay. Bye.
Thank you, Professor.